there's going to be a different way that we're going to do it eventually. But first we're going to talk about parametric equations. And parametric equations, let's see, how do I get that thing to the bottom? Do I have to right click on it? Parametric equations give us another way to represent curves in three-dimensional space. Let's see, that doesn't want, though I guess I can just drag it. All right, there we go. So the Cartesian representation of curves in two-dimensional space and three-dimensional space, if you're talking about surfaces typically, you're very familiar with. That's the y equals f of x, y's and x's that build curves in the xy plane. There is another way to build curves in the xy plane and curves in three-dimensional space, and that is with these parametric equations. And it's important to sort of understand the impetus for why we might want another way to represent curves in two- and three-dimensional space. And let me just give you a simple example. Can you tell me the equation of a line in three-dimensional space? You all know the equation of a line in two-dimensional space really well. You could write it as ax plus by equals c, or you could write it as y equals mx plus b. Now, those are the two typical ways you write a line in two space. How about in three space? Anyone know how you could possibly write a line in Cartesian in three space?
Ax plus bx plus cx, maybe.
Okay, equals d.
Or c is the, something like that.
So you're on the right track in terms of what I would expect to hear. So the simplest equation that you can have is an equation that's linear. Right? If it's not linear, then it's more complicated than a line. So the natural choice then is the hunch you should have is that, oh, well, maybe ax plus by plus cz equals d. That's kind of the generalization of ax plus by equals c. So this one is a line in two-dimensional space, and we're thinking to ourselves, oh, well, if we generalize that idea, we need a z. If we're going to get into three dimensions, we need a z. But you should actually already know what that equation gives you in three-dimensional space. You should have covered it in algebra, or at least talked about it. Anyone know? So that is for sure the simplest equation in three-dimensional space. But do we know what the graph of that is? The graph of that actually is not a line. It is a blank in three-dimensional space.
Vector.
It's not a vector. We don't see any little arrows or anything, so not a vector. So what is that? What is the graph of that in three-dimensional space? Graph of that. So back in algebra, you remember that you were sort of finding intersections. Sometimes you were intersecting lines, and lines intersected in a point, or they were parallel, or possibly they coincided, and they were the same line. And if you did a system, maybe they don't do it anymore. We used to always do it, but maybe we do it. If you did a system with three variables, so you had three unknowns, you had to have three equations, and that corresponded to planes intersecting, or being parallel, or coinciding. So this easiest equation in three-dimensional space is actually a plane in 3D, not a line. So we're thinking to ourselves, well, crap. We do stuff with lines and curves in three-dimensional space all the time. You throw a ball, you shoot a rocket, whatever. You throw a frisbee, right? Those are curves in three-dimensional space. If we can't represent the easiest type of object, and probably the most prevalent type of object that we do, throwing balls and tracking things in three-dimensional space that are on a path, if Cartesian doesn't even allow us to describe that simplest type of curve, we need another system. That's what parametric equations allow us to do. Parametric equations allow us to create the curves and lines and planes that we're all familiar with, but also we can create lines and curves in three-dimensional space. That's why it's vital, because that is the most common thing we do, launch things. So the other thing that is really cool about parametric equations is that you can have an orientation. So in other words, the point, as it's moving through space, is moving in, if it has positive orientation, it's moving in the direction of increasing t. We think of t as time. So as time goes by, you can track where that point is. We'll talk about the t in a second. So, for example, this is what a set of parametric equations look like. Each of the coordinates, sometimes they're called coordinate functions. Each of the coordinates, if you're in 2 space, you have 2 coordinates, an x and a y. If you're in 3 space, you have 3 coordinates, an x, a y, and a z. Now let me just sort of ask you another kind of related question. Can anyone tell me what the graph of y equals 1 looks like? I hear a line.
Horizontal line.
That assumes that we're in 2-dimensional space. When you look at that equation, there's nothing intrinsic about that equation that says, hey, you're in 2-dimensional space. If you were in an algebra class, like in Algebra 1, and I said graph that, many people would go like this. And I would say, oh, well, it's the point at 1. You know? And maybe I should change this to an x so that there's less ambiguity about that. Let's make this an x. So if we said x equals 1, if you're in 1-dimensional space, it's just a point. If you're in 2-dimensional space, then yeah, it's definitely a line. And since I changed it to x, it would be a vertical line instead of a horizontal line. But a line nonetheless. That would be x equals 1 in 2-dimensional space. And if you happen to be in 3-dimensional space, any idea what that graph would be? If you're in 3-dimensional space, x equals 1 would be a plane. So whatever letter is missing from the equation, so if we're in 2-dimensional space, the y is missing, so we grab all the points that have an x coordinate of 1 and y is arbitrary, so y can be anything. If the letter is not in the equation, then there's no restriction on it. Right? There's no y in this equation, so there's no restriction on y. It goes up and down forever. If we come down to the plane, there's x equals 1 right there. And this is going to, usually when we're drawing planes in 3-dimensional space, usually we stick to the first octant. So the first octant is where x, y, and z are all positive. And that plane does go on forever and ever. But same idea here, if we graph x equals 1 in 3 space, we're graphing all the points that have an x value of 1, no restriction on y, no restriction on z. So we've got all these x's of 1, but then all the x's right there are 1. All the points in this plane have an x value of 1, but then we let y be whatever we imagine it to be, let z be anything we want it to be. So it takes on all the z's, all the y's, but x has to be 1. So the moral of this story is you cannot tell the ambient space from the equation. You need more information. Now usually we have context that allows us to see that, to determine that. But with parametric, it's really nice. We see, oh, there's 2 coordinates. That means our ambient space is R2, 2-dimensional space. And we see 1 parameter. So the t is going to be called a parameter, and again, we usually think of it as representing time. And if we were in 3-dimensional space, we would see an x, a y, a z. And if there was only 1 parameter, we would have a curve or a line in 3-dimensional space. And if we had 2 parameters, which you'll do in Calculus 3, you would have a surface in 3-dimensional space. So parametric equations, the number of equation tells you the ambient space dimension. The number of parameters tells you the dimension of the object. Like a curve is a 1-dimensional object. A surface is a two-dimensional object. So if there's one parameter, it's a curve or a line. Two parameters, it's a surface. So in Calc 3, you'll jump from parametric equations in 2 space to parametric equations in 3 space. So how do we graph these parametric equations? The more you handle them, the more it becomes intuitive. But here is the process up here. The first thing we do is eliminate the parameter. So in other words, we turn it into a Cartesian equation, because we are very familiar with graphing Cartesian. So we want to sort of bypass the parametric version of the curve for a moment, get to Cartesian, graph the Cartesian, and then we're going to look at the parameter and see what kind of restrictions there are. And then we'll have the parametric curve, and we can indicate the orientation. So we have to eliminate the t. To eliminate that t, we are going to use the Pythagorean theorem. We know that sine squared of t plus cosine squared of t is 1. Right, that's our Pythagorean identity. Well, we're going to replace the sine of t with y. So we end up with that equation. And we can change the order and put the x's first. So then I always will graph the Cartesian curve with dashed lines. The parametric curve is going to be a subset of the Cartesian. It might be the whole thing, might be the whole entire Cartesian graph, but it could be a subset. It could be smaller. It could be a part of it, not the whole thing. Okay, so we've now done the graph of that. Now we're going to apply the parametric domain by plugging in some points. So now we're going to set up a little table of values. I see the domain here, the parametric domain. So we're going to have t's, and each of those t's is going to correspond to an x and a y. And we certainly want to test the endpoints. And 9 times out of 10, you should also pick a number in between these to test a third point, especially if you have a closed curve. If you have a closed curve and you only plug in 2 points, there's no telling if you're going clockwise or counterclockwise if you just have 2 points. So we usually will pick 3 in most cases, but especially if it's a closed curve, a curve that's, closed. So we plug in our t value up here, and cosine of 0 is 1, sine of 0 is 0. So we're just plugging in t into each place. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of pi is negative 1. Sine of pi is 0. In this particular case, we see pretty clearly that the t, the parameter, is representing the angle, right? The counterclockwise rotation. So this right here is corresponding to t equals 0. This is corresponding to t equals pi halves. And this is corresponding to t equals pi. So we have those 3 points, and we connect the 3. So we did the endpoints of the domain, and then we found a point in the middle because we don't know if we're going clockwise or counterclockwise without that third point. So we are going this direction, and we put arrows not at the endpoints, but in the middle. That shows us the orientation. So in this particular case, there is a very physical, obvious meaning for that parameter. Not always the case. It's not always the case that the parameter is going to have a geometric interpretation that's going to give you information. Many times it will, but not always. Okay, so there it is. So the Cartesian graph is the entire circle of radius 1, centered at the origin. The parametric curve is the upper semicircle, and we have counterclockwise orientation. So, parametric curves allow us to grab pieces of a circle really easily. So, and you can do that in Cartesian pretty easily if you're talking about the specific sides that we're used to, the top half, the bottom half, the right half, or the left half. Solve for x, solve for y, pick a plus or a minus. But parametric would also let you do, oddball parts of the curve, the circle. Like you could easily with parametric say, oh, I want this half of the circle. Like you can't do that with x's and y's very easily. That would be a pain. But with parametric, you could say, oh, we're going to let t go from negative 3 pi over 4 to positive pi over 4, and that would grab that half of the circle. When we think about half a circle, we're always thinking top half, bottom half, right half, or left half. But if we talk about a general half of a circle, a general semicircle, parametric can pick it off really easily, which is super convenient. So that's how parametric equations work, and that's how we are going to deal with them. We will use that exact process. So let's notice that we can have all sorts of different configurations. So the last slide, we had a cosine of t and a sine of t, and we're going to notice that, oh, we can have the same parametric curve correspond to the same Cartesian graph. We're going to use the same identity here. We're going to say that sine squared plus cosine squared is 1. And remember that sine squared of any angle, as long as it matches, this is going to give us 1. So once again, we are going to get the unit circle. And it doesn't matter what the angle is. Sine squared plus cosine squared is 1, as long as those angles match. Doesn't matter. So this tells us that we have y squared plus x squared equals 1. Again, we can reverse the order so it's in alphabetical order if that makes us feel better. And there's the Cartesian graph. Bless you. Now we're going to do the parameter thing. We're going to figure out, well, where are we on this Cartesian graph for different values of the parameter. Once again, we have a closed curve, so we need at least 3 points. If you only pick the 2 endpoints, 0 and pi, well, let's see what happens. So let's just look at 0 and pi for a second. If we plug in t value of 0, cosine of 0 is 1, sine of 0 is 0. And if we go down to pi, cosine of negative pi is negative 1, sine of negative pi is 0. So if we just do those 2 points, we're going to have t equals 0 right there. We're going to have t equals pi right there. But we don't know, to get from t equals 0 to t equals pi, did we go counterclockwise or did we go clockwise? We don't know unless we pick this third point that's in between those 2 t values. That's going to give us our orientation. So plugging in pi over 2 up into these parametric equations, pi over 2, cosine of negative pi over 2 is 0. Sine of negative pi over 2 is going to be negative 1. Okay, so we're down here at 0 comma negative 1 when we're at t equals pi over 2. So once again, we see that the parameter does have a geometric meaning. It's different than the last problem, though. Here, the parameter is representing clockwise rotation from the positive x-axis, not counterclockwise rotation from the positive x-axis, like the last example. And our parametric curve, we're going to connect the dots, and we're going to put in some orientation arrows, not at the end points, but right in the middle. So there is our parametric curve. So same exact Cartesian curve as the last example, but totally different part of the circle, different orientation. Let's look at a third one here. You get the idea. So once again, we're going to use sine squared of t plus cosine squared of t is 1, Pythagorean identity. Now we have x squared plus y squared equals 1. Okay, same Cartesian curve. We know how to graph it. We graph it with dots or dashes because the parametric curve is a subset. Might be the whole thing, might not be. And I think you probably are gathering that in all these cases, if we went 0 to 2 pi, you would get the entire circle. But one would be clockwise and one would be counterclockwise at this point. So let's plug in 0. Sine of 0 is 0. Cosine of 0 is 1. Plug in pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Plug in pi, sine of pi is 0, cosine of pi is -1. So here we are starting at 0, 1. That is t equals 0. Plug in pi over 2. Oh, we're over here at pi over 2. And then plug in pi, we're down here. Connect the dots. So here is our parametric curve. Orientation is always the direction of increasing t. So as t gets bigger, what way are we going? So here we now have the right half of the circle with clockwise orientation. So those three examples illustrate the process of finding the graph of a parametric curve and finding its orientation and sort of understanding how they work. Is there any questions on any of those graphs or how we generated the t-values? This middle t-value, you obviously pick the endpoints, but you can pick any t-value in the middle. Usually we go halfway between. Doesn't matter that you can pick pi over 4, pick 3 pi over 4, doesn't matter. And also, so for this one, again, the t-value does have a geometric interpretation. We see that that t-value is in fact representing angle, but now it's representing a clockwise rotation from the North Pole, from the positive y-axis. That's going to be the geometric interpretation of that parameter. So not always, there won't always be a geometric interpretation, but often there will be. And if we're dealing with objects that sort of are round, an ellipse, a circle, usually it's an angle that it's representing. All right, let's take a look at Desmos for a second. So you can do parametric equations in Desmos really easily. I should have tested that before. Okay, it loaded, good. And this is a good way to just familiarize yourself with parametric equations. So right now I'm doing this cosine comma sine, classic unit circle. And you can see that when a is 0, we're down there. And Desmos is super cool. You can see the orientation as you're going around. And when you go all the way from 0 to 2 pi, you're going to get the full circle. So that's that one. Here was our second one. And we started there and we went clockwise instead. And again, if you go all the way 0 to 2 pi, you get the full circle. You can see the orientation. So Desmos is nice. All you have to do is put things in a vector form. So sine comma cosine, same idea. Starting at the top, going clockwise. And then here is another one that's just a little different. So it won't always be as simple as just changing. Like, it seems so far that, oh, if I just replace t with negative t, maybe that just changes the orientation. And it will sometimes. That will be enough to change the orientation from clockwise to counterclockwise or vice versa. Sometimes swapping the coordinates. So in this third one, we swapped the original coordinates. So the original unit circle is counterclockwise from positive x. And then we swap them, and that changed the orientation here. So this definitely changed the orientation, but it also changed the place that we're starting. So there's different ways to do things. And when we look at this fourth example, we see that, okay, this is going to start over the west pole, start over at the left side of the unit circle and come around. So it's going to give us clockwise all the way around. But if you play in Desmos a little bit, you can help develop your intuition for what parametric curves are doing. So let's look at some non-closed curves. So non-closed curve, come on. Non-closed curve, we still want to use that same process. Let's eliminate the t's, graph the Cartesian with dots or dashes, and then look at the restriction on the parameter and see what we get. And so this one's pretty straightforward, right? If we say that x is t, That means the t is x, so we can replace the t down here with x, and now the t's are gone, and we have a Cartesian equation. Oh, it's a parabola, standard parabola. All right, there is our Cartesian graph over there. So one thing I want you to notice here is that this would be a parameterization that would work for any function. If you have y equals f of x, and you let x be t, and then just let f of x or y be f of t. So in this case, so this is going to be y equals t squared. So if that's a t and this is a t cubed, you're graphing y equals x cubed. If that's a t and that's a whatever, tangent of t, well then you're graphing tangent of x. So if you just let x be, if you have a function, you can just let x be t, and then you can graph that function in parametric. Okay, so there is our parametric, there is our Cartesian curve. Now we want our parametric curve, so we look at our t-values and see where we are and what kind of restrictions we may have. So -2 to 2 for sure, the endpoints. And usually we'll grab a third point in the middle just for good measure. You actually don't have to when the curve is not closed, but it's usually good measure anyway. If the curve is closed, you have to. Okay, so when t is -2, okay, well the x's just match, right? Because x is t, according to the first equation. And then we square all those. So we got 4, 0, 4. So now we come over to our graph, and when t is -2, we are right here. There's t equals -2. T equals +2 is right here. So we already know that the orientation is this way. And then we plug in that middle point just to double check everything. So there we are. So our parametric curve is going to be this portion of the parabola. Now we're going to see something similar to what we saw in the last problem. This parametric curve has the same Cartesian. If we take the t squared and substitute it in here, so take t squared, turn it into x, this becomes an x squared. Same exact Cartesian equation. So let's take a look at our values, our specific values for this parametric curve. Again, we need the t equals -2 and 2. We need the endpoints, but we'll pick one extra point in the middle. Okay, the x's are now 4, 0, 4, because we're squaring t to get x. And then we're squaring x to get y. So that's going to be 16, 0, 16. So when we plug in t equals -2, we're at 4, 16, which is right here. So that's t equals -2. And then t equals 0 is down here. But then t equals 2 is back up at the same place. So this is something we would never see in Cartesian, where the curve is going to trace itself out backwards. So if you're imagining the points being plotted, they're being plotted from right to left first, and then you hit the origin, and then it bounces back and it goes again that way. And so this curve will have no orientation, because it's sort of going in both directions depending on where you are. There's not one direction of increasing t. So this would be, we wouldn't be able to put orientation arrows on this. One thing that you can think of, it's almost like this curve has a hidden cusp. Like in Cartesian, if a function is not differentiable, you can graph it and you can see that there's a cusp or a vertical tangent or a gap. But in parametric, it's not as obvious that this would be this would be non-differentiable. At that point, at the origin there, because we're coming down and then bouncing back, that point right there is going to be a point where it's not differentiable. It's like a hidden cusp. So can't orient this one. With this domain. Obviously, if we changed our domain and we went 0 to 2, we could orient it, or if we went from -2 to 0, we could orient it. If it was going down from -2 to 0, but then it's going up from 0 to 2. So you could break the domain apart into two different curves if you had to figure out an orientation for whatever reason, if you had to make it orientable. All right, so let's look at one that's a little more complicated. Usually they're going to write them sort of horizontally like this. I prefer to write them in this format for a couple reasons. One, it's really obvious how many equations there are. And knowing how many equations there are tells you what space you're in. So here we're in two-dimensional space. It also helps us with the solving because we're using an elimination method or a substitution method. And back in algebra, when you solve systems using those two techniques, you stack the equations. It's just easier to sort of say, oh, if I subtract the two or add the two or do whatever, it's a little more obvious in that case. So I will usually write them this way. Now, when you did solve systems of equations back in algebra, hopefully you figured out that if one of the, if we're going to use substitution, that makes the most sense here. We want to solve for the equation that has the least number of solutions. Right? This equation, if we solved it for t, we'd get a plus or minus the square root of x minus 2. That's not good. You don't want to have a plus or minus in there. So if one of the equations has an odd power, you want to go with that one because there's going to be one solution. So we're going to say, okay, let's solve this one for t. T will be y over 4. And now we'll substitute that into the top equation. So in the top equation, we are going to replace the t with y divided by 4. And now we have eliminated t, so here is our equation. We're going to have y squared multiplied by a 16th plus 2. So we get a sideways opening parabola. The vertex is going to be 2, 0. Now it depends on which college algebra you took, but this would be kind of how you would write it in that college algebra conic form. So the vertex would be 2, 0. X minus h, y minus k. Since y is squared and it's not like y minus 5 squared or something. So that would be our vertex, 2, 0. And it's going to open to the right because this is positive. So that's the graph of our conic parabola there. Now, to finish off the parametric curve, we need to know where we are on our domain. So we're going to do our t, x, and y thing and figure out some points on this parametric curve. So we certainly want the endpoints. So t equals -4 and 4, and we'll pick one point in the middle. So then we look at our parametric curve right there. There's our parametric. Those are our parametric equations. We'll refer to that as a parametric curve, but technically this is the curve. We see the curve, but you can refer to that as a parametric curve, or the equations for a parametric curve. So plug in the -4 into the top equation, we get 18. Plug in +4, we also get 18. Plug in 0, we get 2. So those are our x values. And then we plug our t values into the lower equation, and we're going to get -16. We're going to get 0. We're going to get +16. So this tells us then that when t is -4, we are at 18, -16. So that is right here. So this is corresponding to t equals -4. This, of course, is going to be t equals 0. And this will be t equals +4. So our curve is going to go this way. Put some orientation arrows, the direction of increasing t. There's our parametric curve. So a parametric curve includes the curve and the orientation, and if we have a bounded domain, then we should have dots at the endpoints. So that is our parametric curve. Anything there you are curious about? I'll just refresh your memory down here. So if we have a parabola that opens sideways, the standard equation is x minus h equals 4p times y minus k squared. So if you were graphing it as a conic, h comma k is the vertex, and then we're not finding the focus of the directrix, but that's what the 4p would do. Find the focus in the directrix. Okay, let's take a look at this one. So here, what we've done is made a little modification to our very first example. Our first example was sine comma cosine, or x was, we had x was cosine and y was sine. And we had just the unit circle. So the question is, what does that 3 do? So we know if it's just cosine and sine, the Cartesian curve is going to be unit circle. What do you think the 3 is going to do? Let's find out. So we have our standard Pythagorean identity, sine squared plus cosine squared, in this case of t. That'll be 1. Sine, we look up here, sine is going to be y divided by 3. So this is going to be y divided by 3 quant squared, plus, we look at our parametric equations. If we want to isolate cosine, we divide by 3, so cosine is going to be x divided by 3. Quantity squared is equal to 1. And if we multiply this out, we're going to get y squared plus x squared equals 9. So that's our Cartesian curve. It's a circle of radius 3. So what do we see the multiplication by the 3 does? Takes the unit circle and stretches it to 3. So the radius is now 3 instead of 1. So that is how we can make bigger circles. Now we do the domain thing. We say, okay, we've got t's. Those t's are generating x's and y's. Our domain is 0 to pi over 2. But this curve, this Cartesian curve, is closed. That's not going to be enough to get our orientation. We want to have a third point, so we're going to pick a t-value right in the middle. That's going to make the most sense, so we'll pick a pi over 4. That makes the most sense. You could pick pi over 6 or pi over 3, but usually we just go in the middle. You can be a contrarian, though, and not go in the middle. So plugging in t equals 0 up here, cosine of 0 is 1, 1 times 3, so we're going to be at 3 comma 0. So here we are when t is 0. And we're going to see that we have the same orientation as we had when we had cosine and sine. Bless you. So then we go to pi over 4. Cosine of pi over 4, that's root 2 over 2. So we're going to get 3 root 2 over 2. And the y value, okay, well, when we plug in pi over 4, we get the same thing. Well, that puts us on the line y equals x right there. There's t equals pi over 4. And we're pretty clearly seeing that, once again, the parameter represents the counterclockwise angle of rotation from the positive x-axis. So the parameter in this case does have meaning. Doesn't always have meaning, but in this case it does. It is the positive angle there, counterclockwise. So there is our parametric curve. So parametric curve, graph the Cartesian, and then use the domain to figure out the points in your parametric curve. And then plot the orientation. Any questions on, oh, I didn't put these in here. So pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. 1 times 3 is 3. So there we have our parametric points. Okay. So find parametric equations for the following curves. Include an interval for the parameter values. We want a circle centered at the origin with a radius of 12 generated clockwise with initial point 0, 12. So we're starting, we want to have our, so we're going to have that circle. We want to start up on top, so start at 0, 12. We want the radius to be 12. And we want to go clockwise. So clockwise is going to be to the right. So this is clockwise. So that's what we're looking for. Not obvious. Like we know that the equation of the circle is x squared plus y squared equals 144. That's the Cartesian equation. But we need to start up at the top, start at the North Pole, and we need to go clockwise. So we have a couple of choices. Again, it's not obvious. This stuff is going to take a little bit of finagling. But we sort of are on this kick right now. We know that, okay, the coefficient number is going to give us the radius of the circle. We know that. We know that we have a circle, so there's going to be a sine and a cosine. So we don't know, we know that if cosine went first, that we would start on the east side of the circle and go counterclockwise. So our hunch should be, let's try this. And let's see if we reverse the coordinates, what happens. So we reverse the sine and the cosine, because we already looked at an example of that. And if we think about plugging in our t values, let's just notice where we're at. If we plug in t equals 0, start at 0. Sine of 0 is 0. Okay, good. Cosine of 0 is 1. All right, so we're starting in the right place. That's great. Starting in the right place. Now let's go ahead and pick some other t values. Let's pick, say, pi over 2 and pi. And let's just see if we're going the right direction. So if we plug in pi over 2, sine of pi over 2 is 1. We're going to have that. Cosine of pi over 2 is 0. So we're going to be at 12, 0. Okay, so that's, okay. Oh, that's perfect, right? So 12, 0 puts us on the east side of the unit circle. So this corresponded to t equals 0. This is corresponding to t equals pi over 2. And our hunch is that if we plug in t equals pi, we're going to be at the south side of the unit circle. So plug that in, sine of pi is 0, cosine of pi is 1, negative 1. Negative 1 times 12 gives us negative 12. So then sure enough, we are, that does not like to be touched quickly. So this is going to be cosine, let's see, this is going to be t equals pi, and that point is 0, negative 12. All right, does that make sense? It's not obvious, so if you go to Desmos, if you're not sure, you just start plugging some stuff in. Try sine and then cosine. If we have the wrong orientation, maybe switch the t to a negative t. So there's a few things you can try. If you're trying to change the orientation, common two things to try, switch the x and the y, switch the t to a negative t. Those are two common ways that sometimes will change the orientation. Sometimes it's more complicated, but those are two good tries.
Does it matter where you start, or does it just matter which direction we're going?
Well, this said with initial point 0, 12. So if it tells us where we have to start, sometimes we'll have to do a shift of some sort to get to that starting point. Here we didn't have to do any sort of shifting with the t. Like sometimes you can replace t with t minus pi or pi minus t. There's several things that you'll, as you do the homework, you'll see you might do. So our t values, here we ended up choosing t values. If we want the entire circle, we would go between 0 and 2 pi. Usually we don't put the equal though, because that would overlap and you'd have the whole circle plus 1 extra point. So we usually put a strict less than on the 2 pi. So that'll be the entire circle. So we always include a domain. If you don't include an explicit domain, then the t is assumed to be anything that makes sense. You know, it doesn't cause division by 0 or square root of a negative number or something. The implied domain. So that's called an explicit domain. The implied domain is the set of t for which the functions are defined. So no division by 0 or anything. No division by 0. Let's take a look at lines. So lines, we have, first off, we're going to deal with lines in two-dimensional space, and then this can be extended when you get to Calc 3. You'll do lines in three-dimensional space, and it will just be an extension of the way we think about lines in two-dimensional space. In three-dimensional space, you'll definitely do it with a vector approach, and if you've never done vectors, you can ignore this piece down here, or if you want to figure it out, you can. Before we talk about the vector perspective, we're just going to say these are the two parametric equations for a line, right there. And the pieces there, so if you look at each of those equations, they each look like a y equals mx plus b type of thing, where the x is a t. So, right, they look like where a is playing the role of m, and then t is playing the role of the independent variable, and then that's playing the role of the intercept. All right, so these are going to pass through this point, x naught, y naught. So x naught, y naught is a point on the line. The equation of a line in parametric is not unique. We instantly should be able to recognize that, because if x naught, y naught is just any point on the line, you could pick one point, you could pick another point, I could pick a third, there's an infinite number of choices. Whereas we've seen with Cartesian, if we have a line, as long as we reduce everything, there's going to be one equation, right? If you write it in slope-intercept form, there's one equation. So parametric is a little more ambiguous. There's a lot of choices for that line. And then notice that the slope is going to be b divided by a. So it is the slope, if you will, of this one divided by the slope, if you will, of that one. If you think about the coefficient of the independent variable representing slope, like y equals mx plus b, whatever's in front of the independent variable is slope. So b over a is going to be the slope of the line. And so again, you can kind of imagine writing b over a in different forms. You could have 3 over 1 or 6 over 2, or there's different forms that would reduce to the same slope overall. So before we look at the vectors, let's just sort of try one of these using that concept up above, where we're just told the equations of a line. So as soon as you look at this set of parametric equations, you should be saying, okay, it's a line because each of the coordinates, the x-coordinate and the y-coordinate, are both linear. If they're both linear, you're going to get a line. You can actually get a line even if those aren't linear, but if those are linear, you will definitely get a line. It is possible to get a line even if those aren't linear. We'll see later, but okay, so x naught, that is going to be the constant in the x equation, and that constant is 0. The y naught is going to be the constant in the y equation, that's -4. So 0, -4 is on the graph. All right. And it's alphabetical, right? The x naught from this one, y naught from there, so alphabetical, and then a from there, that's alphabetical, a and then b. So a is going to be the slope, in quotes, of the x equation, which is 2. B is going to be the slope of the other one. So this tells us that m is 2/3. So that is going to be the slope of the line that we are graphing. All right, so now we can graph it pretty easily. So we know that we have a point on the graph, 0, -4. So we are down here, 0, -4. And then the slope is 2/3. So we're going to go up 2 and over 3. So up 2 over 3. That's going to give us another point. And then if we go up 2 again, that's going to bring us up to the x-axis, and then over 3 more, that would put us right 1, 2, 3. Wow, I did not graph that very well, did I? That's supposed to be a line. So 0, -4, up 2 over 3. Bad graph. It's easier to graph the line first, I guess. All right, so up 2 over 3, let's put it right there, and then up 2 over 3, we'll put it right there. That looks better. So there is going to be our line.
Should it be 3 over 2?
So when we look up here, the slope is going to be b. Oh, is that what I did wrong? It's going to be y over x. So slope is always y over x. Oh, thank you. Yes, that is what I did wrong. Thank you, thank you. So just like when you're finding slope in algebra, the x's go on the bottom. The x's act like the picnic table legs that hold up the fraction bar. So x is on the bottom, y is on top. Yeah, I totally goofed that. So this is coming from the y's. So it goes on top. That's coming from the x's, so it goes on the bottom. Yeah, thank you. So let's try again. Let's get rid of that point, get rid of that. So our intercept is down there, 0, -4. And then we're going to go, I did 1, 2, 3. Oh no, I did the other way. Okay, yeah. So there, and then up 3, 1, 2, 3 over 2. So it's going to be that line. There we go. That's better. Okay. Now we haven't found the orientation yet. So we have to look at the orientation. So if we look at a couple of points on here, so if we look at our t, our x, and our y, just to make sure we have orientation, if you plug in t equals 0, you are going to get this point, 0, -4, the y-intercept. And we can plug any other t value we want. We just need one other value. Plug in 1. So plug in t equals 1, we're going to get 2 for x, and we're going to get -1 for y. So 2, -1 is right there. So that tells us that our orientation is this direction. Direction of increasing t. Okay, so that's kind of the memorization way to do this. You just sort of have to remember what goes where. There's also this vector perspective. If you've had vectors, this might make some sense to you. So the A and the B, these slope numbers, we are going to use those to form a slope vector. So that red vector right there, this is going to be the point on the line. So r sub 0 is going to point to the initial point on the line. So this point has coordinates x naught, y naught. And if you describe it as a vector, the vector r sub 0 is the vector that's going to point to that initial point on the line, the origin kind of, if you think about that as the origin of the line. So r0 is the vector that points to the line. So it's a weird thing. When we talk about the graph of a vector function, you're just graphing the tips of the vector. So the graph of r sub 0 vector is really just this point. When we're graphing a curve, a vector value, they call them vector valued functions in Calc 3. So x naught, y naught is going to be that point on the line. And then we form this vector, this slope vector, a comma b. A means go in the x direction, a units, b in the y direction, b units. That forms the slope vector. And then the vector equation of the line looks just like y equals mx plus b, except for vector functions we start with an r to represent radius. So the radial values will be r sub 0 plus vt. And the idea is that as we add multiples of v, if you take a vector v and you multiply it by a constant, you stretch it if that constant's bigger than 1, and you shrink it if the constant is between 0 and 1. And if there's a negative in there, it just flips at 180 degrees and goes the other way. So all the points on this blue line will be graphed for some value of t. If you let t be any real number, it'll take this v and scale it positively in this direction to get everything, scale it negatively to get all the points to the left. So that is the vector way that you could do it if you're comfortable using vectors. If not, you just use the x naught, y naught is a point on it, and b over a is the slope. Either of those will work. All right, let's do one more and then we'll take our break. Okay, so you guys write down those 4 values, right, that you see from that set of parametric equations. So we have our x and we have our y. So write down x naught, y naught, a and b. And then we'll graph it. So x naught 6. So x naught comes from the x equation, and it's the constant in the x equation. Usually when we have a subscript on an x or a y, it means a constant value. So we're thinking of that constant value as being 6. The y constant value, y sub 0, is -3. So that means 6 comma -3 is on the line. So that's the point I've plotted, 6, -3. And then a is the slope from the x equation, -1. B is the slope from the y equation, which is 3, and then the slope is b over a. So the slope is always the slope from the y over the slope from the x. So slope is going to be -3. And you can interpret this in several ways. You could do this kind of thing. So the top is y, so this is up 3, left 1. Or you could go down 3, right 1. Doesn't matter where you put the minus, it just changes the way that you're thinking about it. So I'll use this version right here because that goes left 1, up 3 would put us right there. There's going to be the equation, there's going to be the graph of our line. Right there. And then the only thing that we're missing is, oh, I see that we have a restricted domain. So let's actually deal with that. So we have a restricted domain, so let's see where we're starting and stopping. So -5 and 5 for sure. Let's pick a midpoint. And if we plug in the -5, our start place, so we're plugging in t equals -5, our start point is going to be, that looks like 11 for x. And if we plug in -5 there, we get -18 for y. And then plugging in 0, we get 6, -3. Plugging in 5 looks like 1, 12. So let's get rid of those endpoints. And let's stretch that line a little bit so that we get, is that going to work? We want to go that way also. Okay, so this, in OneNote I can't graph that as dashes, so let's just use some different colors. So let's go with red, that should stand out on the black. So our first point is 11, -18, so we can just kind of visualize where that's going to be. So here's 11, -18, and that is corresponding to our t value of -5. So 11, -18. And then t equals 0, 6, -3, right there. So that's t equals 0. That's t equals -5. And then t equals +5, 1 comma 12. That's going to be up here. So 1 comma 12. That's t equals 5. So our parametric curve is that right there. The direction of increasing t, we're going up to the left. So put some orientation arrows. There's our parametric curve. That is the... Was there a domain on the last one that I missed? Or... Oh, there was. Okay. Well, I will deal with that domain after we take our break. So any questions on how we use the domain to find our start point and our end point? Then orientation is the direction that the points are plotted. So it's the direction of increasing t. All right, let's go ahead and take our break. And I will go fix that one and add the orientation and the endpoint. So line segments can be found by restricting a line. Now, if we want to start from scratch, we've got to be a little more careful. So we want to create the line segment that connects those 2 points. And it says starting at this point. So that's going to be our x naught, y naught, wherever we're starting at. Okay. And then A is going to be the distance to get to the terminal x value. The terminal x value is 2, so A is going to be 2. Going from 0 to 2, 2 minus 0 is 0. 2 minus 0 is 2. B is going to be to get to the terminal y from the initial y, it's going to go up 8. So this tells us that our slope is going to be 4. It's going to be 8 divided by 2, which is 4. And this tells us that our initial point is 0, 0. Okay. So the equations are going to be x equals, so what do you think we're going to put for that equation? How many t plus 0? So 2t, whatever that is, plus 0. And then y is going to be plus a 0 also, so 8t plus 0. So let's check. So there are parametric equations. We need to figure out our domain. So the domain says that we're going to start at 0. If we start at 0, we're going to be at 0, 0. And where do you think we should end?
2. 1.
1. If we use this parameterization, when we plug in 1, we're going to get 2, 8. Now notice, if we reduce the slope, we could also do this. If we start this at 0, that's going to give us 0, 0. And if we stop at 2, won't that give us 2, 8? Yeah. So there's 2 different parameterizations. There's going to be an infinite number always, but here are 2 different parameterizations for the same exact line segment, going from 0, 0 to 2, 8. So notice that the 4, 1 thing is from right here. If we reduce this slope to 4 over 1, we could use the 4 for the y, the 1 for the x, and that will give us a different domain. Domain will go 0 to 2, though, instead of 0 to 1. So if you build your A and your B like this, where the A is basically 2 minus 0, and the B is 8 minus 0, if you use that whole distance for A and the whole distance for B, your domain will always be 0 to 1 for a line segment. So every single time it'll be 0 to 1 if you do that whole thing. But if you reduce it, then you're going to have to increase your domain, your t value, your t integral. Now I forgot to put here we're not dealing with a closed curve, so we want to put that less than or equal to on the 2. For a closed curve, we always have that strict inequality so that we don't overlap by a single point on the circle or an ellipse. So on a closed curve. All right, you all try this one. So find the parametric equations for this line segment, starting at -1, -3, and finishing at 6, -16. Find those parametric equations. Hunt them down. Hunt them down.
I saw you stand there.
So if we're starting at -1, -3, x naught and y naught should be -1, -3. So pretty straightforward there. And then a is going to be the distance to get from x equals -1 over to x equals 6. So algebraically, you could treat it as 6 minus -1, and you are going to end up with 7. 6 minus -1, so we're going to go 7. 7 to the right. And then b is going to be starting at -3 and getting up to down to -16. And the algebraic way that makes it simple is to just do that one minus that one. So -16 minus -3 is going to be -13. So our parametric equations, the simple version is just to go straight across x equals x naught plus a t. So -1. And I don't know why they don't write it in, the form. Whenever we write mx plus b, we put the constant at the tail. And we put the slope in front. I'm not sure why they tend not to do it that way here, but it doesn't matter. You can write it either way. Commutative law of addition. So -1 plus 7t. And then our second constant is -3. And our second slope is -13t. And t, you can use whatever notation you want. So that just says t comes from the interval 0 to 1. Let's double check. When we plug in t equals 0, we're at -1, -3. Plug in t equals 1, we're going to be at 6 and -16. So make sure you somehow indicate your domain. So t is an element, Greek letter epsilon for element. So, any questions on that? Not too bad for line segments. A little easier than infinite series. Well, we've just introduced this new type of curve process, graphing a curve using parametric equations instead of Cartesian. The first thing you learn in calculus is how to find the derivative. In other words, the slope of the tangent. We want to do the same thing for our parametric curves. We want to find the slope predictor function. We want to know what the slope is at different places. It's not that hard. All we have to do with our parametric equations is differentiate each with respect to t. That's all we have to do. So we come down here, and I'll rewrite these stacked. I find it easier to just keep track of everything. So we've got our parametric equations right there. All we have to do is take the derivative of each. Derivative of cosine is minus sine. And of course, we're differentiating with respect to this new independent variable t for each of them. So x prime is with respect to t. Y prime is with respect to t. And this tells us then that our dy dx means slope of tangent. We're going to do the y's over the x's just like we normally do with slope and all that stuff. So y's over the x's. And if you wanted to, you could reduce this to a single trig function called cotangent of t. Now, the one thing that we need to be paying attention to is that dy dx in Calc 1 is always a function of x. Y is a function of x. But here in Calc 2, when we're dealing with parametric equations, we're noticing that dy dx is now a function of t. So we've got to be a little bit cautious, just pay attention. So they ask us to find the slope at that t-value. So the way we find the slope at that t-value, we usually notate it this way. So we're going to say dy dx when t is equal to pi halves. So we're going to do something like that to indicate that it's, we can't just put parentheses of pi over 2, because which we could do if we were finding at an x value of pi over 2, but we're finding the slope at a t value. So this is how we notate it. So it's going to be negative 8 times cotangent of pi over 2. So cotangent of pi over 2, you can go back to here if you don't want to think about cotangent. Like in my mind, I can think about cotangent pretty easily. It's x over y up there at pi over 2. X over y is going to be 0. But if you can't visualize that easily, just come here. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So you have 0 over 1, which is 0. So whatever works, totally fine. So that tells us that we have a horizontal tangent. Right? When the derivative is 0, you have a horizontal tangent if you were to graph it. So that is what the derivative is equal to where?
At t equals pi.
At t equals pi halves, and if we wanted the Cartesian ordered pair for where that tangent line is, how would we find the Cartesian ordered pair? We're going to plug it back into the original set of parametric equations. That tells us where we are in terms of x's and y's. So if we wanted to find the ordered pair x comma y, we're going to take the pi over 2, plug it in here. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So 0 comma 8. That's where this tangent line is. Now I want to actually, I feel like I want to do a little more work on this one. Let's just graph this because this one is interesting. It's a little different. Okay, so let's try to get a visual for this stuff. We have a horizontal tangent at 0 comma 8. We have a cosine and a sine, so if we're going to eliminate t, we would use the Pythagorean theorem. So we know that sine squared of t plus cosine squared of t is 1. Sine is y divided by 8. So if we square that, we're going to get y squared over 64 plus x squared equals 1. What kind of curve is that?
It's an ellipse.
An ellipse. If you have modified denominators so that they're not the same, if they're the same, you have a circle. If those denominators are modified, then you have an ellipse. And if we go to graph this ellipse, we know that it's centered at the origin because it's just x and just y. It's not x minus 5 and y plus 2. Right? It's just x, just y, so the center is the origin. You look under the y's and take the square root, and that tells you how far you go vertically. So we're going to go up and down 8. You go under the x's, that tells you how far you go left and right from the center. So we're going to go over to -1 and over to +1. And there's our frame for the ellipse. So the ellipse is going to be, now there's no restriction on this, right? There's no domain restriction. So we actually are going to get the full ellipse, since there's no restriction. That little 1 is, let's move that so that we can read it. So there's the ellipse, and we just calculated over here that our slope, whoops, why do you vanish? The slope at the slope at 0,8 is 0, and that's because we have a horizontal tangent line up there. Let's move you. So there's our horizontal tangent line up there at 0,8. So there's the picture of what we're dealing with. So you plug in the angle into the original parametric equations to get the location, and plug the angle into the derivative to get the slope. All right, let's try another one of these. So we have parametric equations. Let's stack them, generally easier to keep everything clean. So our derivative system, if you will be 2, 3t squared. So dy dx, slope of the tangent line, is going to be y prime over x prime, which is going to be 3t squared divided by 2. So that is our derivative function. But again, weirdly, it's a function of t, not a function of x, like it always was in Calc 1. So if we want to find dy dx at a particular t value, we're going to notate it like this. That tells us that the slope of the tangent is going to be 3/2 when t is -1. So where is this? At what ordered pair? So what is the Cartesian ordered pair? -2, -1. So we take this t value, and if we plug it in right there, that'll generate the ordered pair that we're investigating. So that ordered pair, t is equal to -1, so t equals -1 generates this slope at that point. And if we wanted to graph this, we could. Solve this for t, plug it into the second equation, we can figure out exactly what it looks like. Or go to Desmos and graph it as 2t, t squared, t cubed would also work. Okay, so find the equation of the tangent line to the curve at the corresponding t value. Very similar, so we just didn't finish off, we didn't find the equations of those tangent lines that we just discovered. So here's a picture of our curve over there, our parametric curve. There's our parametric curve. We can find our derivative system. We take the derivative of both x and y with respect to t. So we got that. Then we can form dy dx. So dy dx will be y prime divided by x prime. So that's going to be 3t squared plus 1 divided by 2t. There's our derivative function. And once again, we notice it's a function of 2. So if we want dy dx at 2, we plug that 2 in, we get 13/4. That's our slope. Where is that slope? That tangent line has slope at, what's the ordered pair that we're dealing with? $310. So 310 we get by plugging that t-value of 2, we plug it in right there, and that's going to give us this point, 3 comma 10. And now we know that the tangent line, which is right here, oops, now we know that the tangent line, really? So is that going to turn into a line, or is that too crooked? Oh, man. There we go. There's our tangent line. That tangent line has slope 13/4. If we want the equation of the tangent line, we're going to do the y minus y0 equals m times x minus x0, slope, point slope form. It's the easiest way to find the equation of that line. So the point we now know is 3 comma 10, so it's going to be y minus 10 equals the slope, which is 13 divided by 4, multiplied by x minus 3. And usually we want to put this in slope-intercept form. So we're going to have 13/4 x minus 39 over 4 when we distribute here. And then we have to add 10. And if we add 10, we will end up with a tangent line equation of 13/4 x, turn that into a 40 over 40, a 40 over 4, so plus a fourth. So that's our tangent line. And clearly from the graph, if you extend that tangent line down, you can see that it's going to cross at 1/4. Clearly. How's that graph is so precise? It's crossing at 1/4. Any piece of that that's not jiving? So another one. Let's stack these first. Writing them as a system I find very helpful. So there we go. This ordered pair you find by plugging in t equals 0. If you plug in t equals 0 here, e to the 0 is 1, so you're going to be at 1 comma 0. So that's our point of interest. That corresponds to t being 0. Our derivative system will be e to the t, comma, or y prime will be derivative of that, 1 over t plus 1. And then dy dx, y prime over x prime. So y prime is in the numerator. We're going to divide by e to the t, and if you want to, you can think of it as e to the t over 1. Flip it, and our derivative will be that. That is our derivative function. dy dx when t is 0 will be 1.
Natural log of 2.
Say that again.
Oh, sorry, natural log of 1. So
Natural log of 1, which is 0. Oh, no natural logs. The order, yes, the ordered pair is at 1 comma 0.
Right.
Yes, I know what you're saying now. Yeah, so our line then will be y minus y0 equals m times x minus x0. So y minus 0 equals the slope, which we just found to be 1, times x minus 1. So y equals x minus 1. So that is the tangent line. Let's see. Yeah, that makes sense. Y-intercept is -1, slope is 1. Yeah, that makes perfect sense, actually. Not too bad. A little easier than testing the endpoints. A little easier than a binomial expansion. A lot easier. Fine way to finish on something that's not as hard. Okay, this is a little harder here, arc length. So arc length, in earlier renditions of arc length, we had a very similar looking integral, but it was the integral of a square root of 1 plus the derivative squared. 1 plus y prime squared. So the only difference is that instead of having a 1 plus y prime squared, you have to take both the f function, take its derivative and square it, and the g function, take its derivative and square it. Why they introduce new letters is a little bit of a mystery. Why not just use x's and y's? All right, we have our parametric equations where we have x equals and y equals. We take our derivative, we have x prime and y prime. We can just use those. We don't need to call those a whole different letter. We don't have to introduce an f and a g. So this is the way I would look at the equation up there. So instead of this square root right there, I would just treat it like that. It's a little easier to remember. It's just the square root of the sum of the squares of the derivatives. Okay, so here's something that we talked about long ago. When you look at a curve in the coordinate plane, if we've got a curve, come on, why are you so sensitive? So we've got this curve, and we're looking at a point on this curve. There was the differential triangle that we talked about long ago. Differential triangle. If we go ahead and pick 2 points on the curve, we can say that this is dx, this is dy, oops, not dy, that is delta y. And if we draw our tangent line, I know I clicked you. All right. If we draw our tangent line right there, so we always have that the independent variables, differential and increment, are always the same. So dx is the differential, delta x is the increment. The vertical piece here, that's exactly the vertical distance between those points, that's an increment. Increments is always exact. Differential, when we're talking about our independent variable, is the same, but when we talk about the dependent variable, that distance right there is dy. Right? So the slope of the tangent line is dy over dx. The slope of the secant line is delta y over delta x. The delta y is the full vertical distance, so it's not on the tangent line. Delta y goes up to the curve. So delta y over delta x is the slope of the secant line. If we were to put a secant line right in here, there's our secant line. So that one has slope delta y over delta x. Whereas the tangent line, good grief, don't quite understand that. That has slope dy over dx. Right. And then this distance along here, that distance along there is ds. All right, so ds is the hypotenuse of the dx dy triangle. And ds squared will be dx squared plus dy squared. We take the square root, take the positive square root. So that is what we are going to replace ds with, that. If we could measure along the curve, we could, but we don't have those s values. ds is the arc length differential, so ds needs to be converted because we don't have s limits. If we had s limits, it would be easy, so we convert the ds to a dt. Just like back in the beginning of the semester, we changed the ds to a dx, or sometimes to a dy. So we have to turn it into something that we know how to manage. Okay, so there's our differential triangle. And just for completeness sake, if we were to measure from between these two green dots along the curve, that would be delta s. That would be the exact arc length along the curve would be delta s, but we would need s values to calculate that. So we use the ds. All right, so let's try it. We're going to start with the simple one. A line. That's a line because both are linear. So I'm just going to stack them just to make it a little more visually consistent with what we've been doing. So there's our curve, our parametric curve. And then we find the derivatives of each of the coordinate functions. So we have that. This tells us that dy dx, if we were asked, is 4/3. So that also tells us that we're dealing with a line, right? Because it's got a constant slope. Okay, so we want arc length. So arc length, s, is going to be the integral on this interval 0 to 2, the square root of 9 plus 16 dt. So we integrate the sum of the squares of the derivatives. All right, that's 25. We end up turning that into a 5, so we have this. So what is our final answer? 10. So we know by now that if you integrate a differential on an interval, you get the length of the interval. So we get 5 times 2, which is 10. So that is how we're going to find the arc length of a parametric curve. Let's try another one. So here we have circle of radius 3. Notice that this one is not centered at the origin. Notice how we shift a circle. So we have 3 cosine t, and then for the y, we don't just have 3 sine t, we have 3 sine t plus 1. So you can see, I think, that we shift up 1 unit. No horizontal shift because the cosine is all by itself up here without a shift. So whatever we add to the, so if we just had 3 cosine and 3 sine, we'd have the circle centered at the origin. And if we add something, we just shift it. So there we go. There's our parametric curve. Let's get our derivatives. So derivative here is minus 3 times sine of t. Derivative here is 3 cosine t. And if we want arc length, in other words, we're finding the perimeter of the circle, the circumference of the circle, whatever. So arc length, we'll call it, oh, well, he was calling it L, wasn't he? Not just S, he was calling it L. Some books call it S, a little less. So we're going to go from 0 to 2 pi square root of x prime squared. So 9 sine squared of t plus y prime squared, 9 cosine squared of t, dt. Nine sine squared plus 9 cosine squared is 9.
Oh, yeah.
If we factor out the 9, we have a sine squared plus cosine squared, which is 1, and then 9 times 1 is 9. So we end up with the square root of 9, which is 3. Integral 0 to 2 pi dt. And what's our final answer there then? 6 pi. So that is our arc length, our perimeter, our circumference. You could also say, hey, this is a circle of radius 3. Circle of radius 3. Perimeter is 2 pi r. 2 pi times 3. So you can also see it that way. Okay, this one's a little bit different. Looks like we're going to find, looks like, now, all bets are off that this is really a circle. It certainly looks like a circle, right? But we have not proven that this equation does not look like familiar in terms of a circle, right? We've seen cosine and sine with the same coefficient in front. How could we show that this is a circle? We would have to eliminate t and get the Cartesian equation, and it should be some shifted circle. Or, oh, it's centered at the origin, so we should get an x squared. If it really is a circle, we get x squared plus y squared equals a constant squared. So you could try that to see if it really is a circle, or maybe it's just a little squashed. We'd have to prove that. But it doesn't matter for us. We're just finding the derivative of each. So the derivative of x with respect to t will be negative sine of t. Derivative of sine is cosine of t, so we have that. Derivative of cosine down here is minus sine of t plus cosine of t. So there's our derivative. Now we're going to have that nasty square root of x prime squared and y prime squared. I'm going to square these separately just to not make too much of a mess. Yep. So we're going to FOIL that all out. So this has to get multiplied by itself. So negative sine times negative sine is sine squared. And then we have to do this one times this one and double it. So that's going to be positive sine cosine, but we have to double it. And then we have to take that one and square it, and we get plus cosine squared. Similarly down here, we square the first term and get sine squared. And then this one times this one doubled, so minus 2 sine t cosine t. Oh, it scared me. It stopped. And then cosine squared of t. So our arc length formula says that we're going to have L equals the integral from 0 up to pi square root of x prime squared plus y prime squared dt. So we need to add these two things together, which we can kind of come over here and just add them. If we add them, we are going to get 2 sine squared of t. The middles cancel, plus 2 cosine squared of t. And what does that all equal? 2. So if we factor out the 2, we're going to get a 2 multiplied by sine squared plus cosine squared. So 2 times 1, so we'll get a total value of 2. So that allows us to then write this as the integral from 0 to pi square root of 2 dt.
It's just a constant.
And we're going to get a constant, so we'll get square root of 2 multiplied by pi. That will be the arc length. That'll be the arc length from between those 2 points. So, if this was a circle of radius 2, to find the circumference, we would do 2 pi r. So we would go, right, 2 pi r, the radius appears to be 2 here, if this is really a circle. And what's 2 pi r then? 2 pi times 2 is 4 pi. divided by 2 is 2 pi. That's square root of 2 times pi. So is that thing a circle? No. That is, or at least it's not a circle of radius 2. Certainly it looks like that point, though, would make the radius 2. But if you look carefully, it looks like this is... Well, I guess that distance right there is not 2. It looks like a circle of... What does it look like? Circle of radius 1. Looks... Oh! No, what does it look like a circle of?
1.4?
Yeah, I'm high. No, I'm not. Joking. No, I'm not. I was thinking of I was measuring diagonals. We don't measure diagonals, right? This is 1 right here. That's 1. That's 1. So what's that distance?
Root 2.
Root 2. Root 2. So it looks like a circle of root 2. So if it's a circle of root 2, the circumference would be pi times r squared, which would give a, no, not pi r squared. What is it, 2 pi r? 2 pi r, circumference formula. So 2 pi r, so that's 2 root 2 pi. And if we wanted half of it, we would divide that by 2, which is what we did get. So it looks like it's a circle centered at the origin of radius root 2. Okay, so it does look like a circle, where that radius is square root of 2. Yeah. All right, that's a weird looking circle. If we want to prove that it's a circle, we'd have to eliminate t here, which is going to be a little bit of work, but it's possible. It's possible. I dare you. Dare you. Polar coordinates. Final topic. Polar coordinates. Polar coordinates are another way to describe the points in a plane. So we have the Cartesian description of points in a plane. You go horizontal, go vertical. Polar, instead of going horizontal and vertical, you rotate and then head out in that radial direction. So this point right here, x comma y, we went horizontal and then vertical. If you do it in the polar fashion, you rotate and then you go out. So you go r comma theta. R tells you the distance to the origin, it's the radial value. And then theta is always counterclockwise from the positive x. So if you look at this triangle, there are 4 natural equations. You have x squared plus y squared equals r squared, which is that one. You have cosine of theta, which is x over r, and if you solve for x, you get that equation. Sine of theta is y over r, and if you solve for y, you get that equation. Tangent of theta is y over x. So you do sine, cosine, and tangent of theta, and you get 3 equations, and then you do the Pythagorean to get the 4th. These equations take you back and forth between a Cartesian representation and a polar representation of the same point. Okay, so those are the equations. Now, there's a couple of weird things with polar. Obvious polar point is where everything is sort of in standard form, so r is positive, theta is a positive angle, so you're rotating counterclockwise. Obviously, if you add multiples of 2 pi, you end up back at the same point. That wouldn't be the standard representation. The standard representation will always have theta between 0 and 2 pi, but it could represent the same point. And then here is the weird thing. If r is negative, which it can be in polar, it means that you bounce 180 degrees in the other direction. So if the theta happens to be, let's say, pi over 3, and the r happens to be negative 2, you end up down here. You just go down that terminal ray into the opposite quadrant, and you go whatever the distance r is. So we call r a radial value as opposed to the radius, because it can be negative in polar. So let's take a look at some examples where that can come up. So here we have a bunch of points in the polar plane. Let's describe them. So let's grab one of these points. I'm going to grab F. Let's take a look at F. So what we want to do is describe this point. So point F, I'm going to describe it in polar. Sometimes we'll put a little p down here to emphasize that it's polar. It's usually obvious from the context, but you could put a p there just to make sure that you know that it's polar. And remember that in polar we do r comma theta. So r comma theta. That's the order that we use. Okay, let's look at F. How far is F from the origin? All right, well, it's this distance from the origin. We're at 1, 2, 3, 4. So I'm going to first do the standard representation. The standard representation is going to be a positive radial value, and whatever that counterclockwise rotation is, that counterclockwise rotation, 3 pi over 3, 4 pi over 3, 5 pi over 3. Everyone agree? 5 pi over 3. So counting by pi over 3s, right, there's, dang it, I changed color. Why are you being finicky? No comprendo. So there's pi over 3 right there. So pi over 3 takes us to there, then another pi over 3 takes us to there, another pi over 3 takes us to there, another pi over 3 takes us to there, another one takes us to there. So we went 1, 2, 3, 4, 5 pi over 3. All right. That is the standard representation. Now, another representation we could have, for those of us that want to be contrarian, we could say, I don't like rotating counterclockwise. I want to rotate that way. You can do that. This will generate the same point. That angle right there is negative pi over 3. This will be the same point. That's not the standard representation, but it represents the same exact point. Now, let's suppose that we are wanting to choose a negative radial value. If we want to choose a negative radial value, the radial value would be negative 4. We have to have the magnitude be the same. But negative 4, that means that we would want an angle that's up here in quadrant 2. So if we choose the standard angle in quadrant 2 that has this terminal ray right there, that would be
2 pi over 3.
Yeah, 2 pi over 3. So that's another representation in polar, same point. And now if we want to be hyper-contrarian, we want both things to be negative. What would our negative angle be? Negative, so we have to get all the way up to here, so negative 1, 2, 3, negative 4 pi over 3. Yep. So that would take us clockwise around and then go backwards into the opposite quadrant. So those 4 representations, all the same point. This one is the preferred one. This one is the standard representation, where both r and theta are positive. So these are clearly polar points, at least based on what we've seen, because we see these theta value, we see angles here. So now obviously that technically doesn't, it is just a number. Remember that an angle in radians is unitless. There's no units on an angle when it's in radians. When we say radians, we just mean not degrees, because radians come from the equation. We have that S is equal to R theta. And if we solve for theta, We get S over R, and remember S is arc length, R is radius, those have the same units. The units cancel, so theta in radians is a multiple of the radius, and so it's a unitless number. So technically this could be a Cartesian point, 1 comma whatever that number is, but they're telling us that we're in polar. Okay, so this tells us that R is equal to 1 and theta is equal to 2 pi over 3. If we want to convert that to x and y, that's actually pretty easy because x is our cosine theta and y is our sine theta. So if we're going from polar to Cartesian, it's pretty easy. We just plug those numbers in there and simplify. So if we plug those in, here we're going to get that x is equal to r times cosine of 2 pi over 3. And y is equal to r times sine of 2 pi over 3. So for this particular one, we're going to get cosine of 2 pi over 3 is negative 1/2. Sine of 2 pi over 3 is root 3 over 2. So this is going to give us the ordered pair negative 1/2 comma root 3 over 2. All right, because we're on a unit circle, those numbers should look really familiar. Okay, this one, we can do the same thing. We can do the same thing, no problem. So this is going to be, x is going to be r, which is a negative number, that's fine, times cosine of 3 pi over 4. And y will be negative 4 times sine of 3 pi over 4. So there, this is going to give us, let's see, cosine of 3 pi over 4. 3 pi over 4 is right in the middle of quadrant 2, so negative root 2 over 2. So negative root 2 over 2, so that's going to be positive 2 root 2 when we simplify. Sine of 3 pi over 4, that's positive root 2 over 2, divided 2 in, so we're going to get, I said root 2 over 2, so negative 2 root 2. Something's fishy. Oh, it's fishy because r is negative, because that's in quadrant
2.
So this is in quadrant 4.
So I was looking.
This is in quadrant 4. 3 pi over 2 is in quadrant 2, but because the r is negative, the point's actually in quadrant 4. All right, so 3 pi over 4 comes up, but r is negative, so it bounces us into quadrant 4. That's why this Cartesian is a quadrant 4 point. Right? X is positive, y is negative. So if we look at the graph here, 3 pi over 4 is right in the middle, and what was our r? 4. So let's see. So this is 3 pi over 4. It does not like me writing on any sort of image in here. I wonder why that is all of a sudden. I don't feel like it's been doing that. So here is the angle 3 pi over 4 right there. But when we go negative, we come back this way. There's 1, let's see, 2 is right there, 4 is right there. So we are right here. So this is the negative direction. So that's why we're going to get that quadrant 4 point. So these are the coordinates of that point. Now going the other way is harder. So express the following Cartesian in polar. This is harder. Finding Cartesian is easy because the formulas have x and y isolated already. So you just have to plug in the r, plug in the theta, and kind of blindly multiply them. So that's easier. So here we have a little more work to do. So we know that the first one we usually will find is r, because r squared is x squared plus y squared. So we know that r squared is going to be 1 plus 3. So r will equal plus or minus 2. All right, so normally when we're dealing with a radial value, we always choose the positive, but in polar, you don't have to. You can be contrarian and get away with it. Now, tangent is how we find the angle. So we would say tangent of theta is y over x. So here we're going to have tangent of theta is root 3. And what is next takes a little bit, we have to just be a little careful. Trig equations have an infinite number of solutions. Right, all trig equations have an infinite number of solutions. When we say tangent is root 3, when we look at the unit circle, there are two possibilities when we are looking at the unit circle. Tangent is root 3 at these two places on the unit circle. This theta value, the standard theta value, is pi divided by 3. So technically what we would say is that we would get a reference angle, and then we have to go back up and look at our quadrant to make sure that we pick the right angle. Now in this case, we're in quadrant 1. All right, we're in quadrant 1, so we know that we're going to pick pi over 3. But you have to be a little careful right here. You've got to look at your picture, because if you just write theta equals inverse tangent of root 3, that's going to find the reference angle, not necessarily the correct theta. So you just have to be a little careful there. So in this case, everything's lined up fine. We're going to get pi over 3. But let's suppose both these were negatives. If both these were negatives, we know that we would be in quadrant 3. So if we did the inverse tangent of this, we'd get pi over 3, and pi over 3 would then be measuring this reference angle right there. And so we would have to add pi to it. So we just have to be a little careful of the quadrant thing. We'll come across some that we have to be more careful with. So our representations then, the standard representation would be r comma theta. This would be our standard polar representation. That makes sense to everyone? So 1 comma root 3 is right there. We're in quadrant 1, so the theta has to be pi over 3 and not some other, not 4 pi over 3. All right, let's stop there and we will finish this one up on Thursday, and then we'll have our final exam a week from Thursday. Holy smokes! Crazy. A week from Thursday, we are done. Or at least you're done. I have to grade them then. Got to grade them fast. Get them graded and inserted.